we are going to delve into the chemistry and the chemistry and physics of what makes our diodes work, and specifically we want to live right here in this area of the periodic table. There's lots of reasons: carbon, silicon, germanium, tin. Not tin so much, but this area: aluminum and phosphorus and boron, gallium and arsenic. Um, uh, I guess this is tin over here. I forget. Is this selenium? I'm not a great periodic table person, but the reason why this column is so important is this is valence 4 electrons, meaning our Bohr atom model has 4 electrons that are floating out there, ready to covalently bond with whatever's next to it. Okay, and that's important for this because it sets up our crystal structure, and we'll talk about that here in a second. But what's really interesting about this is relatively new. And by relatively, I mean, well, this is called the Solvay Conference. This meeting that happened in 1911. Very famous meeting. And just to give you an idea, here he is right here, Albert Einstein, but not to be outdone by people like Schrödinger. Okay, Schrödinger equation, Heisenberg uncertainty principle. Very brilliant man. Marie Curie, Lorentz, of course Einstein was there, Bohr, Niels Bohr, and half of these people went on to get the Nobel Prize. These were the brilliant people at the turn of the century, and they discussed basically how atoms work, and they started to understand very heavily about this valence 4 electron in quantum physics. And there are some fights. Einstein does not like quantum physics at all. He did not like it at all. And it's better understood today, but it's still, there's some things about the electron not being there till it's observed. It just drove Einstein nuts, and entanglement, which also drove him nuts because it seems to violate the speed of light. But the one that we're interested in right now is silicon. And there's some other important characters in here. Aluminum here at number 13, phosphorus, germanium, arsenic, and gallium. And what we want to do is we're going to make what's called a crystal. And so let me see if we can silicon tetrahedron. Let's see what we can come up with for an image. So because we're at a this is more of the chemistry stuff, but if you could get silicon to crystallize with itself, it's a tetrahedron structure, meaning it's that 4-sided dice from Dungeons and Dragons, and it can align with itself. And if we can get all the atoms to align in a single formation, we get all of these triangles to be in perfect alignment, and they will, and they can, and we can do this. But you need extremely pure silicon. Funny enough, right outside of Butte here, at a facility, they're able to make extremely pure. It's called float zone silicon. It's so pure. It may be the purest of one kind of atom stuff in the world that they create, just miles from where I'm sitting. And so, but it gives us a tetrahedron structure. In the book and in other places, they just say silicon lattice, and they call it a square lattice. They do it in 2 dimensions just to give us a better, so this is a good example of a silicon lattice structure, but it's actually 3-dimensional, it's not 2-dimensional. And maybe this one is even a better one. Let's see if we can find one that's bigger. And they even doped this one with something like boron. And so what we're going to do is we want to look at, and these are all really teeny tiny for some reason, but this is showing you the covalently bonded atoms right next to each other to create what we call a lattice structure. And this is what gives us our semiconductor properties, the powers that we would hope that they would. Specifically, that we can go in, and so this is an example of a 3-dimensional lattice. And so I don't want to spend a lot of time on this, a lot of time on what it physically actually looks like, but we need to have very high quality, very high purity silicon in order to do this. And so we're going to do just exactly what they had there. We have a whole bunch of atoms of silicon. Silicon is a semiconductor. Semi meaning it's a large truck that drives down the road. No, semi means it can conduct when it wants to, or it can't conduct when it wants to. These have each two electrons that bind them together, and we end up with covalently bonded pairs, and it makes a structure. Funny enough, you can see the structure in the macro world if you chip a block of silicon that's relatively pure. You can see in the macro world what orientation the crystals are, which is actually pretty cool. And so these are all +4, okay, +4 electrons, and they're bound out here with 2 electrons each to make, okay. And so far this looks really boring, but what we want to do is we want to measure on this approximately how can we move electrons through here? And the answer is yes, we can. And the reason why it does is because this is how it would look at absolute zero, at 0 Kelvin. T is equal to 0 Kelvin. If we get above that, what happens is one of these electrons someplace there'll be enough energy in thermal energy in there to bump one of these electrons to make them free. Okay? And so now we have a single bonded, and maybe there's another place over here where we only have a single bonded. It's not covalently bonded anymore. Co means 2. And we have this electron here goes and floats over to this spot here, takes over, and maybe that's enough energy to pop one out. So we have free electrons, okay? And so we're going to call that number n. Okay, that seems really boring, but that is the number of free electrons that the free electrons are going to be there, and it's going to be temperature dependent. There's also going to be P. These are going to be, so these are electrons. Yes, these are called holes. These are the absence of electrons, okay? And so we should have an intrinsic, so intrinsic is a big word. An intrinsic silicon. Intrinsic means no impurities, perfectly latticed. It just looks beautiful. An intrinsic silicon, N should equal P. In other words, the number of electrons that have popped out are the number of holes that are floating around in there or that want to be in there. This is different than copper. Copper has more electrons than it knows what to do with. And so we can continuously shove electrons in, and it shoves electrons out. This is different. This will suck in electrons and pop them out as we put them, but it always has the same number. In fact, we call this number Ni for the number of electrons in an intrinsic piece of silicon. Intrinsic means not doped, means pure. Pure silicon, perfectly latticed. And we can calculate this. Not surprising, temperature is going to be a factor. But Ni is equal to B times T, which is the temperature, over 3/2, however that comes out. B, once again, is going to be is a constant. It's the band gap energy. Okay, so we're going to have to define that. And then this is going to be E to the Eg. Sorry, Eg is the band gap energy. E sub G over 2 kT. And so we have two temperatures that work in here. K is going to be our Boltzmann's constant once again. And let me see. B is just a material-dependent parameter. Okay? So it's a fudge factor. That's what they did. They made a fudge factor. So we're just going to, for silicon, this is for silicon, is 7.3 times 10 to the 15th centimeters per centimeter cubed. And then Kelvin to the minus 3 over 2. Okay? And then, let me see, band gap energy, 1.12 electron volts. Boltzmann's constant. Which one are we going to use? Okay, this one is 8.62 times 10 to the negative fifth times 10 to the negative fifth electron volts per Kelvin. And you can see if our temperature is 0, that's going to wipe this out. It's going to make it all 0. 0 Kelvin, obviously that makes a lot of sense. And so what we find out, what we want to do is we want to calculate this for something that's at room temperature. The question is, how many electrons, how many free electrons are there in a cube of centimeters, a cubic centimeter of silicon? So I'm going to come up here to MATLAB. We're going to put in these values right here. B, I'm going to put in as 7.3 e to the 15th. Okay. K, we're going to put in as 8.62 e to the minus 5. We're going to put in Eg is equal to 1.12. We're going to put in, let me see, the temperature is equal to, in this case, we're going to do 300 Kelvin, and I think that's all we need for this entire thing. So Ni is equal to B times T. Oops. T, 2 with 3 over 2. Sorry, I lost my screen. Okay. Lead to the 3 over 2 times the exponential of negative E. Oh, I forgot that over here. Negative Eg. Okay. Good thing I checked. Negative Eg over 2 times K times T. And we get, in this case, 1.5 times 10 to the 10th. And this is in units of per centimeters cubed. So this is carriers per centimeters cubed. And so this is Ni at room temperature is about 1.5 times 10 to the 10th carriers per centimeter cubed. Okay? What does that mean? That means at room temperature in a cubic centimeters, there's 1.5 times 10 to the 10th electrons floating around in there. And maybe they're getting bonded or not as it goes through. But the fact of the matter is that they're in there. Okay? And the problem that we have with this is we have no real idea of how many atoms there are in a cube of centimeter. And let me solve this for you. This seems like a lot. Okay? But the number of atoms in our silicon, in the same block, is 5 times 10 to the 22 atoms. In the same, I'm going to try my hand at a cubic centimeter. In the same block of silicon, there are 5 times 10 to the 22nd atoms. That's a lot. Look at this, 12 orders of magnitude difference. More than 12 orders of magnitude difference. And so, as far as this goes, what is that? 5 times 12. 5 times 10 to the 12th. How big is 5 times 10 to the 12th? That's huge. So that's like saying, okay, if we were to put, that's like one person on the Earth. As far as if you could populate the Earth evenly with people around the outside, just giving you an idea, if we could populate cover solid Earth so there's no water and put a whole bunch of people in there, that all of them, there would be one atom for all of those people around the globe. That's kind of the scale that we're talking about here. We're talking about lots and lots of not a lot of electrons. So the electrons probably never even see each other, but they're close enough together that they can feel each other. That's how strong these potentials are. In other words, they can push against each other. That's what's kind of interesting about electrons, is this seems like a lot, but it's not a lot. Okay. So that's kind of interesting. Let's introduce something called the mass action law. This is one to keep down. The number of holes times the number of electrons
is equal to Ni squared. Well, duh. For intrinsic, this is true. But what happens when we dope material? So this is one you want to put in there. What happens when we add extra holes or extra electrons? We're about to do that. We need to start doping. And so what this means is we add in some kind of contaminant in with our silicon. What we want to be able to do is make very small changes in how many electrons or holes are there, so that so in doped, P will not equal N. In intrinsic, we already said this, P was equal to N. So let's start looking at this. So we can dope stuff to be N-type, meaning it's more negative, electrons. There are more electrons than holes. Or P-type, positive type. There are more holes are greater than electrons. Electrons greater than holes. Okay? So we can dope it to be P-type or N-type. And we use both of these, okay? And so let's see. All that happens here is, and once again, the amount of doping that we're doing, fill up the world with people on the very outside, cover it with people, and one of those people is a dopant, okay? Or 2 or 3, not many for the entire world. But here, we're going to put it in a valence 5, okay? Valence 5, such as going back to our periodic table, and I'm not going to show it to you, but the periodic table, that should look something like, valence 5 should be arsenic or phosphorus, okay? But that gives us an extra electron that's floating. It's still covalently bonds, but that extra electron is floating out there, but there's no accompanying hole, okay? So that means that so there's an extra electron floating out here. That's going to give us N-type. So in a weird thing, phosphorus, if we dope with a phosphorus atom, one atom for this, it's going to give us N-type phosphorus, just so that we're not confused. We can also dope a separate piece of silicon with something that's valence 3. Okay? And that means that we're going to be missing that gap right there, which means, I'm just going to say H+. We have an extra hole. Okay? There's a gap there. One of these has an electron on this side, but not on the other. And it doesn't need to be next to the dopant. In that case, boron is going to give us something called P-type. And this is a new concept. It's kind of hard to understand, but it's very critical for us to understand that we can dope it and get different ratios of N to P. Okay? And so if we have N-type, which means we have extra electrons, it's negative, remember. So we say N sub N is approximately equal to N sub D, or they use capital D for the subscript. And this is the number of donor atoms, okay? And what they're saying is when we dope it, approximately the number of spare electrons in there is approximately equal to the number of donor electrons. It's not exactly, because we still have those free electrons from the Ni, the intrinsic electrons that are floating around out there, but typically this is much, much bigger. This value is much, much bigger than Ni. And so it's actually, so N is actually going to equal Nd plus Ni. But Nd is much, much bigger than Ni. Okay? And so we can make this approximation that these are approximately equal. Okay? And this subscript here, that little n, means that this is an N-type of material, because we also are going to have a P-type. There's still going to be a number of holes in there, but it's in an N-type doped piece of silicon. I know this is all kind of just floating around in your heads, but that's when we're going to use our mass action law. N times P is equal to Ni squared. This number has not changed. Okay? So P of n times n of n is equal to still ni squared. This number has not changed. It's still, for room temperature, 1.5 times 10 to the 10 to the 15th, 10 to the 10th, 1.5 times 10 to the 10th. And so we can get an idea for what this is. And so we'll do an example of this here. We can also have p-typed material. So in the p-type, we're going to say P sub P is approximately equal to N. A is for acceptor. Okay? So it's approximately equal to the number of acceptors. Same kind of thing. We can have a whole bunch of spare holes in there. So those holes are actually turned into charge carriers. It's kind of weird, but that's the way it goes. And imagine those games that exist, the penny games in a Cracker Jack box, where they have a square in here, and then they have a whole bunch of tiles, and then one of the tiles is missing and you have to move them around. Well, if you have a whole bunch of those missing holes like this, things can move more. And so that's why we can call the holes a carrier, a majority carrier or carrier in this. And so because of this, we end up with the same thing on this side. There's still an NP, which there's still going to be electrons floating around there, just many, many fewer than holes, times P sub P is still going to equal Ni squared. And so that mass action law comes up, and so we can calculate this all through if we would like to. And depending on how much dopant is in there, and so the amount of dopant that you're going to be given, like how many atoms of dopant per cubic centimeter are you going to be giving? And that's kind of one of those problems. So let's do an example. We have an N-type piece of silicon, so N-type. Okay? Nd is equal to 10 to the 17th per centimeters cubed. That's how many phosphorus atoms they injected into a 1 cubic centimeter block. We want to know how many electrons are there, or approximately how many electrons. Well, we're going to go back and look at this, and what they said is Nn is about equal to Nd, so that's easy. Okay, but I also want to know what P sub n is going to be. This is going to be Ni squared over Nd, or about. It's going to be about this. And this turns into 1.5 times 10 to the 10th squared over 10 to the 17th. Turns out that Pn is going to be rather small. And so I'm going to go back over to my MATLAB. And I can get there. And so now that we have Ni already programmed in, I'm going to say Nd for this one is equal to 10 to the 17th. Okay, Ni to the second divided by Nd. Oops. There we go. Not many at all. Look at that. We could practically count the number of spare holes that are in there. In fact, we probably could count those in not too long if we could have an electron microscope that goes in there and finds all the holes, or whatever. We could go in and count the actual holes that are in there. 2.232 times 10 to the third. Not many at all. So it's really just not that much. And thus, in a doped piece of silicon, the majority carrier is going to dominate. Okay? So that's our first delve into semiconductor physics. Without the charge carriers, either N-type or P-type, the electrons, the current isn't going to flow very well. Okay? And so that's why this is a semiconductor. If we dope it more, the electrons will flow more. But we can't change the dopant of a material in the midstream of creating a in our device. So in other words, if we have a block of silicon, we can't change how many electrons and holes are intrinsically in there, or are bound in there. But we can manipulate them with electric and magnetic fields. And so that's how we end up doing this within there. So we can manipulate how they behave over time, and thus we can make something look like a resistor at one point, and a short circuit at another point, an open circuit at another point. by applying the right voltages and currents to it. So that's what we're going to get to in the next video.